Hey there, me again, researching lubricants, specifically how to lubricate potentiometers. And I found some interesting information, general street smart information from experience from people like that, but also book smart stuff. So let's take a look at all of those and see what I've discovered. As you can see, I have scoured internet. All of these purple things is what I've opened. I've read lots of stuff. Do potentiometers need grease? I've taken a look at this article, and there's lots of information. So let's see what we have. I've watched 1 hour 26 minutes long video from this guy, detailed potentiometer servicing info by Retro Electro Tech Vintage Audi Restoration channel, and he goes into great detail about literally everything, the protection, everything. I love this. And essentially, it all boils down to using silicone grease. That seems to be the best thing to do. So let's talk about it a little bit. So you're going to see that, let me just play this video. He's actually using this fine tip to apply silicone oil. And you can watch his video to see what exactly he says that he's using, but it's silicone oil essentially. And he's applying it to this track. He's going to apply it to the metal. Let's just speed it up for you, to this metal part. And then he's also going to apply some grease on this metal part. Specifically, he's going to apply the grease here. Let's speed it up. So as you can see, he's explaining a lot. And then he takes some silicone grease and he applies it to this metal housing. So let's put it down and let's quickly talk about. And you can see he's also lubricating this part. So let's see what happens here. So let me explain really quickly what's happening with potentiometer. You have the housing. This is the bottom part of the housing. This is the top part of the housing. You have the conductive part, and then you have this shaft with this metal stuff on it. This metal stuff rubs against this conductive part, and that's how you get resistance. So let's go one by one and really quickly explain what should be lubricated how, based off of this video. So you have the bottom metal housing. This is where you put silicone grease. So grease, it's thick, it's not going to run away, it's going to stay there. Why? Because this plastic shaft, and by the way, this shaft can be made out of plastic, as you can clearly see, but it seems that it can be made out of metal. However, I am unsure if only the part you grab with your fingers is made out of metal, or the entire thing is made out of metal. It would make sense that the entire thing is not made out of metal, but we'll get to it. So, because this plastic part will rub against the metal housing down here, you need to apply some silicone grease here. Why silicone grease? Because it seems that silicone grease is the safest thing to use on plastic, anything that's made out of plastic essentially. But I'll show that as we progress through the video. We'll slowly go from street people smarts, and we'll slowly progress to book smart. So you take whatever you want. This is what I've discovered so far. In the comments, please do write if you have any more details or more precise knowledge. So you apply silicone grease here because this plastic part is going to rub against this metal as you rotate the potentiometer. Obviously, you rotate your volume knob. It's going to rub there, so there's going to be some friction. Every time there is a friction, some type of friction, with any type of tools, electronics, it's a good idea to lubricate these parts. So that's what's happening. Any mechanical parts that create friction, it's good idea to lubricate them because they're going to rub against one another physically. So in this case, we have plastic rubbing on metal. So you're probably already noticing how it makes no sense for this part, this shaft, I believe that's what it's called, to be made out of metal fully. Maybe only the part you grab with your fingers is made out of metal, so only this little part over here. But everything else is going to be plastic because like you clearly just noticed, it's going to rub against one another, so it makes no sense for it to be metal on metal to create extra friction. It makes more sense to be plastic, so that's what's happening there. But let's try to find a photo of more of these disassembled and see if there's anything made out of metal specifically. Because once again, you see these metal thingies, these golden metal thingies, they are also made out of metal. So if the shaft was going to be metal and this is metal and the housing is metal, we're going to have a short. So essentially everything will be shorted and it's not going to work properly. Let's try to find more disassembled really quickly. So here is one potentiometer made out of metal. As you can clearly see, the part you grab with your fingers is made out of metal. But look at this, everything else is made out of plastic. So I believe it's clearly visible. Look, it's clearly plastic. Now, there does seem to be, look at this, it's clearly plastic. So metal, and then underneath we do have some plastic parts or whatever these things are. It's clearly not metal, essentially, is what I'm trying to say. We do have some, you know, this is blacks, maybe some black type of plastic. Maybe he didn't even disassemble it. I'm not sure what kind of potentiometer this is exactly. But you can see this clearly doesn't seem to be metal. And even though over here we do have metal thing that we grab with our fingers, the rest is made out of plastic, as you can see. Once again, here is another potentiometer. And you can see that the part you grab with your fingers is made out of metal. But if we keep scrolling down, look at this. This black stuff seems to be made out of plastic. Right there. And here's the metal part you grab with your fingers. Clearly made out of metal, obviously. So hopefully we gotten that out of the way. It seems that this thing is made out of plastic, so that's what's happening there. That's where the friction is going to happen. Next thing, we have this part. First, the brown piece seems to be just some type of board or some type. It seems that its purpose is just to hold everything in place. It's just sort of a foundation. I'm not sure what is it made out of, but in this case it doesn't matter. What matters is, I believe, is this black track. Let's call it like that. This is a track, and I'm going to explain why really soon. It's going to all fall together. Just bear with me. So this track is, it seems that it might be made out of carbon or some type of conductive plastic. How can plastic be conductive? Pff, beats me. Is that what carbon essentially is? I'm not sure. It might need research. So essentially it seems that it all falls into one. It's essentially the same thing. Conductive plastic is engineered, so it's a material that's filled with a conductive additives. So it's filled with something that is conductive. Traditionally, this is accomplished through use of carbon fillers. So it's filled with carbon, such as carbon black, graphite, and other conductive elements. So it seems that this is just essentially it's carbon. No. Obviously, I'm not a chemist. It's not really. But, you know, chemists are going to be mad at me. But essentially, for our sake, it's just carbon. So let's just call this a carbon track. Now, it should also be lubricated with, seems like, silicon oil. Why lubricate carbon? Well, beats me. Well, actually, there is something in the book which we will discuss. To my extent, to some type of knowledge I have, carbon itself should be self-lubricating. No, I'm not sure, honestly. I don't know. I'm not an expert. So just disregard that. So what matters is there's going to be something in the book about this. Why should you lubricate this part? And let's keep moving on. So what's happening here is that, let's move to this shaft. It has this metal golden piece. And see over here, it sort of extrudes. All of these things are attached to plastic, but look how over here it seems to be, you know, pushing up a little bit. Or over here as well. So these things, actually I believe these things over here, are what's going to rub against this carbon track. So these things over here, or these things, I'm not sure which one are extruding a little bit. Yeah, it definitely seems that these things are what actually rubs against the carbon track. As you can see, it is pushing up a little bit, and it does have some black deposits on top of it, so it clearly that's what's rubbing against it. And you're going to notice that he is going to clean it. He actually puts something like a pen underneath it so he doesn't break it, so he can apply some pressure while cleaning these things. So right here you can see how he's going to clean everything, and specifically he's going to put some extra attention to these things. So he's cleaning them. Let's see. Let me speed it up. So he's cleaning everything. Let's take a look really quickly. So you can see that he cleaned these things, so they're very shiny now. And this is what is actually rubbing against the carbon track. So because it's going to rub, this is metal, essentially on what we said, it's a mixture of plastic and carbon. It might be a good idea to also lubricate it so it doesn't get worn out too fast. But there is another reason, and let's keep talking about all of this. So next, because we have this, essentially this part that is sticking out, it has to go through this part. You also have to lubricate it right here. So you're going to notice that he takes this plastic shaft, he lubricates it, but he also takes the metal piece where the shaft is going to go through, and he lubricates it with the silicone grease. Now let's take a look at this little handbook, the potentiometer handbook. This seems to be the only handbook I was able to find on how to do everything with potentiometers, how to make them, how they're constructed, all these things. So if you're interested in details, feel free to check it out. But there's something we are interested in, which is grease section. So you're going to see how it explains how everything is, moving against one another. You can read all of these things if you want, but let's take a look at this. Lubricants are commonly used on metal and 𝐎𝐼𝐹 elements. So I'm not sure what this 𝐎𝐼𝐹 is. Is that what is the mixture of plastic and carbon? I don't know. So you can read what this 𝐎𝐼𝐹 thing is. So 𝐎𝐼𝐹 is composite material consisting of ceramic and metallic materials, hence the 𝐎𝐼𝐹, whatever I said. Ceramic in general has high temperature resistance and hardness, and the metal has the ability to undergo plastic deformation. 𝐎𝐼𝐹 is ideally designed to have the combined optimal properties of ceramic and metal. And if we take a look at is 𝐎𝐼𝐹 better than carbon, the lifetime is very short for carbon, just several hundred movements for carbon. In comparison, 𝐎𝐼𝐹 lasts much longer, up to 50,000 movements. And by the way, I love this notebook. Look at this. What is this made out of? What was it? 1975, baby. 1975. I love this. So not only does this freaking handbook show you the machine that this thing is made, it actually shows you how it looks like when this resistive material is printed on the potentiometer. Look right here. You can see. Let's zoom this in. Look right there. Here's the potentiometer. Literally, this track is being printed on it, and it explains how it's done. And look at this badass beast doing the job. The cement ink is fired in a temperature controlled kiln, whatever this is. Look at that. Everything. Look right here. That's the thing right there. So it explains everything. But I digress. We were talking about lubrication. So we have lubrication, commonly used metal and 𝐎𝐼𝐹 elements to prevent oxidization, so noise will be low. That's why we are lubricating this surface as well, that's made out of carbon or 𝐎𝐼𝐹 or whatever, so we do not have oxidization, so noise will be low. Mechanical life is also increased, which is especially important for precision. The lube reduces wiper and element wear. So there we go. Not only is this wiper thingy, so this thing here, I suppose that's what's called a wiper. Right here, this metal part that's rubbing against, wiping against this. And element wear, and acts as a vehicle to contain minute wear particles during extended mechanical cycling. So that's what's happening as well. Potentiometers, I suppose just these, like I've said, these particles, because it's going to rub against one another, the particles are going to stick to the grease, and, maybe they're just going to stay around, not going to bother. I don't know. But let's keep reading. Potentiometers used in servo systems are required to respond faithfully during the first sweep of the element, even after sitting dormant in one spot for long periods of time. So if your potentiometers are not used for long, if you don't use, for example, your radio volume knobs, even if you lubricate them, it's going to be good. Look at this. A lube will help assure this type of performance. There is no one magic lubricant that can be used at potentiometers that will meet all requirements. The anticipated operational environment dictates the type of lubricant. So it really depends on the environment. Is there going to be low temperature? Normally, a type of light silicon oil lubricant can be used. Is there going to be high temperature? Here, a silicon type grease. So you can see silicon oil, silicon grease, we're there. Can be used. Low viscosity oils may tend to migrate away from wear areas at high temperature and may not be acceptable. Essentially, potentiometers should not get very hot. Still, it is a form of resistor. So, pick your poison. Outer space vacuum applications, dry lubricants are generally used. So we have these things. There we go. There are certain dry lubricants, molybdenum, whatever this is, are very effective at high vacuum and outer space. So there we go. Many potentiometer manufacturers have their own special property lubricants. These generally consist of various silicon fluids and greases prepared to their exacting specifications. So yeah, you can keep reading, you can find this book. Really quickly, let's just touch on these particles because these things are going to rub against one another. So let's read the contacts part. The wiper has a significant effect on many potentiometer parameters. Contact resistance, CRV, maybe this is noise ratio or something, I'm not sure. Oh, it's not something else, I don't know. What is CRV? So CRV seems to stand for contact resistance variation. The apparent resistance seen between the wiper and the resistance element, so the track and between the wiper, when the wiper is energized with the specified current and moved over the adjustment travel in either direction and constant speed. Yeah, I suppose. So maybe it's something like, you know how your mouse has the acceleration? So if you move it slowly, it's gonna. I'm not sure what exactly. I don't know how this translates to real life. It doesn't compute with me. Resolution, noise, power rating, operational life, and stability. All are all influenced by the design of movable contact. Before discussing the factors related to contacts used in specific potentiometer design, consider what happens when two electrical members come together or make contact. Here's the drawing that shows you what's happening. Over here, you have, I believe the A would be the wiper, and B is the conductive material, that is the carbon track. So you can see when they come together, you can see this is magnified view. You can see it clearly says magnified view of contacting surfaces. You can see they're not smooth at all. But although the surfaces may look smooth, an extreme enlargement, so right here we can see zoomed in, of the interface reveals a non-uniform contact. The members touch only where the high points of member A meet the high point of member B, so right here where they meet. And the area where two members are actually touching is only a fraction of the apparent contact area. However, another important factor is illustrated in figure 723. All metal have film of oxides, sulfides, blah, blah, blah. There we go. So even if thoroughly cleaned, the films will quickly reappear. On base metals such as copper and aluminum, these films can form to a thickness of 50 angstroms, whatever. It's a very small unit of measurement, I suppose, in a few minutes. They continue to grow until they are several hundred thingies thick. One more thing, even though they look like this, you can see how at the beginning they look like this. Let's really quickly read. Certain factors can improve electrical connection between two members. So friction generated by sliding action can abrade a portion of the insulating film and smooth the surface to increase the effective contact area. So as we move the wiper, it slowly rubs against. Both of them actually rub against one another, and slowly the surface gets smoothed out. There's not going to be this. And now you can start to see why the carbon track, or whatever this track is made out of, why we lubricate it. Because not only is it going to prevent oxidization, it can also improve the contact, the life, the durability, all these things. And thank God for this little book. And thank God for the past. It seems that everything in the past was way better. You get way more information. Today, these noobs are withholding information. Come on, you bastards. So I've scoured the internet to find what greases are available today exactly. I mean, it really matters if it's a silicon type of grease. But there's a bunch of greases you can find online. People use these for these potentiometers, and they might work. However, I have a potentiometer which is extremely rare, and I cannot purchase it anywhere. So I have to be very careful to what I apply to it, so I do not damage it. I want to prolong its life. Yes, at one point I will have to purchase a replacement, but right now I have the original. It's in very good condition, and I would like to preserve it with proper lubrication. But by withholding so much information, I simply cannot purchase these products that are displayed and used. Maybe they work for most people, but most of the times these people make... so here's what happens. You're gonna find a bunch of articles made by people and or whoever. So right here you have potentiometer maintenance and lubrication case study. And there is an outline what they will do. Dismantle it, clean it, lubricate it, retesting, and the analysis and all these things. So you can see how much noise there is really quickly. Let me show you the noise. You can see how the noise looks like. Look at these lines over here. Just compare this to this. Look how nice and smooth it is. There are no crazy lines all over the place. Those lines are what is noise, essentially. And this is when it's cleaned, lubricated, and works fine. Look at this right here. Also nothing crazy. Look. Just nice, smooth lines. So this is after, and this is before cleaning and lubrication of the track itself. You can see crazy stuff happening. However, one thing, and you can see they really disassemble the whole thing. They show you everything. Beautiful. However, one thing that really concerns me is how all of these articles and stuff like that. They will tell you what they did. They might even provide you with a tutorial, what type of grease they used. By the way, if you search for this grease, if you search for what the material datasheet says, they withhold the information as well. But you can see how it looks like. Sort of reminds me of silicone grease. I don't know. Anyways, you can see how it's very, yep, looks like silicone. Anyhow, if we keep looking through this, even though they will sort of, I don't know what this shows improvements and all this stuff, they never report back after 2 years of 1 year maybe of opening the potentiometer to see how the state is. Is the plastic in fine condition? Did it disintegrate? What happened with the carbon track? Are the dirt deposits, the particles, are they around it? Are they on top of it? Did they do more damage? So these articles never report, or not just articles, but videos, anything that's made by general users or even research, what they state here. Still, there is no, report after 2 years, maybe 1 year. There's no feedback after that. What happened? Can you provide an update? There is no update whatsoever. So that's why I cannot rely on these specific brands if they are withholding information like we have seen. Here is somebody recommending 𝐅𝐎𝐋𝐋𝐖. What is that? That might not be available in where I live. What the hell? So look at this. It says multi-purpose precision lubricant. Every time I read something as multi-purpose, I instantly think of WD-40. And take a look at this. It says plastic safe. Well, let's see what's happening. Here is material safety datasheet for this particular lubricant. 226 multi-purpose precision lubricant. And if we scroll down to composition, information on ingredients, the section 3, look at this. Distillates, petroleum. But didn't you say that this is safe on plastic? Well, petroleum is not really safe on all plastic, just some. So look at this. We have, because some plastic is essentially made on the basis of petroleum, as far as my understanding goes, but throughout the series I will explain more as I learn more. And I've learned that the best way to establish your knowledge is to explain it to somebody else. Explain what you have learned, and that's how say it out loud. That's one thing. I don't know. Anyhow, we have petroleum, then light mineral oil. But mineral oil, that's what petroleum is essentially. It's a mineral oil. Again, we have petrolatum, which I believe this is the synonym for petroleum jelly. Petrolatum is FDA-approved skin protectant. Aha, interesting. It is available over the counter in its concentrated form, known as petroleum jelly. Or maybe Vaseline. Might remind you of a God's loophole. All right, I'm moving on. Anyways, like I've said, this thing, multi-purpose precision lubricant. Every time I read multi-purpose, I think of, oh wait, not Vaseline, WD-40. Look at this, multi-use, multi-purpose. Sure, find a different way to say the same thing. Good, great job. If we scroll down to section 3, LVP, aliphatic hydrocarbon. But look at the CS number. 64742478478. Let's go back. 647424778. But isn't that just the distillates for petroleum? Oh no. So it's the same thing, just differently named. Oh, great. So you can see how they use the same thing. Petroleum-based oil, and then aliphatic hydrocarbon. Oh, but it might be the same thing. I don't know. But why? Look at the CS number. Look how first 5 numbers are all the same. It might all essentially be just petroleum or something that's based on the petroleum. In our case, doesn't really matter, because if something is based on petroleum, it can damage plastic, which is based on petroleum, because petroleum and petroleum tend to mix together. Hydrocarbons, these bonds, or however the chemistry works. I'm in the process of learning chemistry just for the sake of this. Hell yeah. But we'll have to learn. And look at this, carbon dioxide, 2 to 3%. And if we go back, carbon dioxide, 1 to 3%. So you can see how these products seem to be similar. So how is this safe on plastic? Go ahead and spray it on PVC type of plastic. See what happens. Your doors are made out of PVC. See what happens. So that's what's up. And as an icing on the cake at the end, I found this little booklet. Quick study for product design engineers. And if we scroll down, they explain essentially what the lubricants are, what's happening there. So you have oil lubricants, what they do. Then you add thickeners to them to make them thick, to make them like a grease. Then you add additives to increase their performance, maybe in low temperatures, high temperatures, to protect from corrosion, all these things. And then you have solid lubricants. And they have some analysis of temperature and stuff like that, viscosity, all of these things. But here we get to the nice little graph which says a guide to oil plastic compatibility. So there we go. And you can see what oils you have and what types of plastic. Are they compatible or not? Mineral oil, like for example what we've just witnessed that petroleum is. It's a mineral, essentially. That's what the mineral oil is going on here. For example, PP plastic, polypropylene, it's yellow, may or may not work. For lots of other plastics, you'll be fine. But there's a couple of plastics which you will not be fine with. So you can see, or you may or may not, test it out on yourself and see if it's worth ruining your equipment for may or may nots. So there we go. But if we take a look at silicone grease, we can see that silicone grease seems to be fine with every single piece of plastic. So we should be good there. And you have some other types of plastic, PAO plastic, which seems to be similarly compatible like mineral. And then we have PFPE, which I'm going to explore in the future. What is this? This seems to be compatible with everything. Why I say everything? Well, let's scroll down. Look at this. We have another graph. Guide to oil elastomer compatibility. So if you have something that's elastic, essentially, there you go. So you can see how, once again, silicon is compatible with almost everything except stuff that's made out of silicon. Remember how I've said, look at this, fluorosilicon rubber and then silicon in general? So that's what silicon is not compatible with. Generally, because this is all chemistry, essentially, boiled down, simply alike stuff tends to mix. That's what seems to be the consensus here, what I'm noticing. So silicon will mix with silicon. So if you use silicon grease on silicon something, it's gonna melt, disintegrate, dissolve. Essentially, they are mixing. The molecules are mixing together. That's what's happening on chemistry level. So that's what's happening. You can see what the compatibility. And you can read like a general, just summaries or whatever this is. So PFPE, look at this. Again, it's compatible with all elastomers thingies. Oh, interesting. So we might take a look at this. So this booklet's very interesting. Then you have these thickeners, what's happening there. You have more information. So really worth checking out. Really useful booklet. Thank you, whoever these guys are. We're going to look for more of these. But that's the knowledge I've discovered so far. So generally, for potentiometers, silicon lubrication seems to be the best. And it's going to be icing on the cake if silicon actually does not attract dust. You've seen in my previous video, I've shown you that some say it does, but literally in the same sentence or later, it doesn't, it does. What's going on? Are you people even in contact with reality? Do you even see what you're writing? What did you use? Did you use the artificial intelligence to write this article? What's going on? We're not going to discuss that. We don't care. If they have contradicting information, that means they are unreliable. We're going to scratch them out, cross them out, and not even bother. So that's what's up. It took them 40 times to make WD-40. That's what the WD-40 stands for. It took them 40 times to get to the formula. It clearly is going to take them 40 times to write a good article that makes sense. So we'll let them try to do that as well. Anyhow, this is the information I have for you right now. As far as potentiometers, we're gonna test silicon grease in one of the future videos. I do have I actually need to go purchase a silicon grease. I do not have it at the moment. I do have silicon product that's used for silicon caulking product, whatever that is for, for windows and stuff like that. But it hardens basically. It becomes really hard after some time, so you don't want to use that as a lubricant. It's essentially a sealant. So that's one thing. So, but we can still, I believe, test it to see if it attracts any dirt. But I'm also going to purchase silicon grease and test it. And I'm going to provide you with a safety data sheet, the ingredients of the grease that I purchase, if it's available. If not, well, shit. So we're going to see what happens, man. Really interesting journey. After that, so right now what I'm focusing here is sort of trying to get the knowledge on the basis of what I have at the moment. I know I am not chemistry wise. I do not have chemistry knowledge or knowledge about atoms, the molecular bonds, and all these things, what's polar, what's non-polar. I did research, but it's still, I do not have that type of brain yet. I'm not thinking like a chemist yet. So as this series progresses, as I learn more and more, I will try to explain it as simple as possible, because like Einstein said, if you cannot explain it simply, then you do not understand it yourself at all. And that's what's the motto of this video series. Those losers can explain shit, so we're gonna have to do it for them. But luckily we have these compatibility charts and whatnot, so that's it. Oh, one more thing, I still want to just really quickly showcase this website as well. It seems to also have a graph of material compatibility. I'm not sure exactly, does this refer to, yeah, look at this, silicon, again, not compatible with silicon, so it seems to check out for the most part. So yeah, but it requires more research, so take it as you want. Like I've said, as the series progress, hopefully we get more opinions chimed in, as well as facts, checked stuff, research stuff. And yeah, as the series progresses, I will have more specific stuff, but I will also try to focus on general knowledge as well. So that's it. Thanks so much for tuning in. See you when I see you. And remember, if you cannot explain it simply, then you do not understand it at all. Noobs. Goodbye.